Everybody for coming. Today is the final seminar in the series on history of science, technology, philosophy and mathematics. Welcome. And today's speaker is from our own Faculty of IT at Monash University, and Kevin Korb's interests are in artificial intelligence and the links between it and philosophy, and that is the subject of today's presentation. I'll leave it there and welcome Kevin. Thanks.
Okay. I'm also interested in artificial life. That was the original inspiration for these talks, actually, was Alan's working on a book on the history of A life, or the prehistory of A life, if you like, before it was called that. So I've taught artificial intelligence for 20 years here at Monash, and have a history with it a little bit longer than that. So I've engaged in various disputes, directly or indirectly, and so I'm going to talk a bit about some of the controversies in and around AI, beginning in some sense anyway with Dreyfus. So this is the cover of Dreyfus's second edition, What Computers Can't Do. His third edition, he struck out in a new direction. The title was What Computers Still Can't Do. So what do you reckon? Are computers stuck here? Yeah, this stops them cold, right? Well, this was written before laptops and before long life batteries, so it's not clear that this is such a huge problem any longer, particularly with the innovations in robotics that Ray is working on and others. Okay, so history of artificial intelligence. AI is a degenerating scientific research program. I thought that was a cool and spiffy title when I came up with it. I had completely forgotten that Hubert Dreyfus had already used this expression to describe AI before. It's, of course, not really that great an innovation for anybody who knows anything about philosophy of science. Anyway, so I was reviewing just a couple days ago, actually, a bit of what Dreyfus had written on this subject. I haven't read him for 10 years previously, or reread him for 10 years previously. So I'm going to talk about Dreyfus's objections to artificial intelligence. He stated them in, forget the abstract, sorry, I meant to have that deleted. He stated them in a very absolutist kind of way. And I found them highly objectionable, but I'll try to restate them in a somewhat less absolutist way today and more or less accept them, actually. So, a bit on the history of AI and the disputes concerning it. Artificial intelligence, of course, was invented by Alan Turing. Again, perhaps that's not such a great innovation. If you look at the history of thought back to the Greeks, they certainly were creating machines, as Alan Doran has been investigating, and from the very early days they thought about thought and what it might take to recreate it. So it's not a great leap from having the first genuine general purpose electronic computing device to the question of how you can get them to behave intelligently. So even before those computers were available, McCulloch and Pitts famously invented, in some sense, the first artificial neural nets. So this is a kind of drawing they used to portray them. In effect, what it is a logic circuit. So in the first case, what we have, I mean, they describe these as neurons. It's an abstraction of what they conceive the brain, how they conceive the brain to work. So these are some input neurons labeled A and B. Here's an output neuron. There's a bifurcation of the axon leading into the soma of the output neuron. What that means is that you basically have a double weight of the input on A, a double weight on the input of B. There's a threshold of 2. If the threshold is achieved, the neuron fires. So that, of course, is an OR gate. If either A is on or B is on, you get an accumulation value, some value of 2 or more, and it fires. And here's an AND gate, and here's an AND gate. This is being a negation. So they were developing finite state automata, and effectively saying, or putting forward the thought that this might capture much of what the brain is doing. So those were the first artificial neural nets, and the artificial neural nets today generalize on that. During the war, and immediately after, Turing began testing the claim that machine intelligence is possible. In the first instance, partly out of his own personal interest, he did it by inventing the first chess program and testing it in his hut with the computer available to him, which was his brain. He operated it and played a little chess with himself, so to speak, or with his algorithm. Also around that time, by his own report, he started arguing with psychologists and philosophers about what intelligence might be. His aim being to make the case that the computer devices he was working on in some future incarnation where they become more powerful could actually challenge humans for the claim to being the most intelligent on Earth. Okay, but his disputes, he complained about his disputes with psychologists and philosophers because they never came to any resolution. He had arguments that he figured were pretty compelling, but no one else seemed to be compelled by them, partly because no one had a proper definition of intelligence, and indeed no one still does have a proper definition of intelligence. It's very much like so many other concepts in English or any other natural language. They're extremely hard to pin down. So he came up with an alternative, a behavioral test for intelligence, which was just the imitation game. So can a computer driven by some computer program mimic human intelligence? It's not really a matter of mimicry. People use that word, but that's not really the issue. The issue is whether or not qualitatively over some reasonable period of time with some reasonable engagement with a human, their verbal behavior can't be distinguished from human behavior in a reliable way. So the imitation game. So the idea of the imitation game is, or the Turing test as it's come to be known, is that behind one curtain is a woman, behind another curtain is a computer, and both are pretending to be, of course, Eliza Doolittle. So there's a little representation, and here we have two things pretending to be Eliza Doolittle, one being an IBM 360, another being Julie Andrews. So what Turing proposed was, as a criterion, if after 5 minutes a human interrogator has roughly 50-50 chance of guessing which is the computer, which is the woman, then the computer passes as intelligent. And furthermore, he predicted that by the year 2000, this test would be not exactly passed, but would be close to passing it, and it would be on the way. And furthermore, if you read his 1950 paper, you'll see it's pretty clear that Turing thought that machine learning would be a key to achieving this kind of intelligence. It was part of his rebuttal to critics. Okay, so that's machine intelligence, and then there's also artificial intelligence. What are they? What's the difference? Today, if you ask around the AI community or its, whatever. If you ask around and try to figure out what people mean when they talk about machine intelligence, computational intelligence, artificial intelligence, turns out they're actually different. I don't really hold with there being any interesting differences between them. There are cultural differences, though. So artificial intelligence is more or less the American word for the same thing. But it is associated with this group of miscreants, and it's associated with a certain approach to artificial intelligence, that approach that Hubert Dreyfus was so adamant about opposing, in fact. So John McCarthy, there's John McCarthy, Oliver Selfridge, Solomonoff. We had Solomonoff and Minsky out here actually in 1996. That was fun. And this guy, Timur, I don't even know who he is. I'm no expert on the history of these things, by the way. But this is kind of entertaining. This was at a conference. When was that? Oh, well, okay, so 2006, obviously. This was at a conference 2006 organized by James Moore at Dartmouth. He's a philosopher of science. And he called the conference AI at 50. So AI 50 is dating it 50 years after this conference organized at the same place by John McCarthy to launch artificial intelligence. And you notice this is 6 years after Turing's paper. So they got the date wrong, right? Or it's an American point of view that whatever happens in England, Europe, Africa, Asia, the rest of the world doesn't really matter. What happens in America matters. And AI started in 1956 at this conference. Anyway, so the AI of McCarthy and company is very logic-oriented, especially in the beginning. So perhaps its first most notable success was the general problem solver of Newell, Shaw, and Simon. So they introduced heuristic search and problem solving with symbolic representation in this computer program. They solved a very important problem, Towers of Hanoi, which had been plaguing mankind for millennia before then. And a couple of years before that, they proved a few trivial theorems out of the Mathematica with the related earlier program, logic theories. So anyway, the idea of their approach to artificial intelligence is really theorem proving. I guess that comes best in the next slide, in John McCarthy's version of it, which he called the advice taker. So I'm calling this logicism. In philosophy, logicism meant the idea that all of mathematics could be reduced to logic. And Russell and Whitehead burnt themselves out trying to prove that. And that was because, of course, they were working decades before Gödel proved it was impossible. So logicism died a certain death in the 1930s, and in fact that was also the birth of computer science, because Turing took that proof by Gödel and went and showed that arithmetic is undecidable, and with computer science being the spin-off of all that work. Anyway, so logicism in philosophy is dead, but that doesn't mean it was dead in computer science. McCarthy and others took it up. So the idea here is that intelligent behavior can be reproduced by theorem proving. So here we have a little robot, which is a theorem proving device, and it has two sources of axioms. Actually, I've labeled only this one axioms. That's McCarthy or some other human stuffing axioms into the brain of the theorem prover. And then there are sensors which gather up percepts and effectively another source of axioms for the theorem prover. And the theorem prover takes these axioms and cogitates and eventually out falls a theorem or two. So that's the idea. So if you have a problem you want to ask your advice taker, it's actually advice giver, I guess. Anyway, if you want to ask your advice giver some question, like is Colombia in South America or something, then you give it some axioms about geography, etc., and it tries to prove or disprove that Colombia is in South America, and eventually it either succeeds or fails and something falls out of it. So first order logic sentences are our universal representation language. That's from a true believer, David Israel. I don't give a date here because I've forgotten where the reference came from, but he actually said that. So there are the axioms, you feed them in. The Lisp machine resolution theorem prover is the universal inference engine, and we solve all of our problems. The obvious complaint about this approach is that it's all deductive. Surely artificial intelligence means we have a robot situated in the world, moving around, dealing with uncertainty, trying to generalize, trying to make sense of this strange world that it's been put into. Okay, so it has to do induction, not just deduction. So what about that, Mr. McCarthy? The AT can't learn about the world. McCarthy actually has a response to that. He said, once we know what functions describe learning, we can simply stick them into the AT. Lisp, after all, in Lisp, functions are first-class objects. They can be interpreted, and so once we learn the right thing, we program it. Now, what this response to the request for learning, machine learning, is essentially this. Machine learning is algorithmic. Our system can interpret any Lisp function because it's a Lisp machine, and so machine learning is solved. With the minor problem that McCarthy didn't bother telling us what the function is. So the problem is just open. Okay, machine learning is algorithmic. Fine. Some people will dispute that one as well. I won't bother disputing that. I accept that it's algorithmic. But that doesn't mean that we know what it is, and that doesn't mean that this is any kind of solution to anything. All you're saying is that your advice taker incorporates the universality. Great. Here's another issue. Maybe this has the best claim to supporting my claim, and Dreyfus's claim, that AI is a degenerating research program. Because McCarthy and Hayes posed this problem based on thinking behind the advice taker, posed this problem in the late 60s, and then spent the rest of their careers arguing that everybody else's attempt to solve the problem whacking a situation. So, for example, at 1, 1 means you're at grid location 1, 1 in situation S. And then there are fluents. Fluents will represent actions that map situations to situations. This is how you change the world. So you can move forward in situation S, and then you'll get a subsequent situation S prime. For simplicity, in the next slide or two, I'll just indicate subsequent, the very next situation with a prime. So if you're at 1, 2, if you're at 1, 1 in situation S and you move forward, then in the situation forward S, you're at 1, 2. Something like that. So fluents represent possible changes to the world caused by the agent. This is a very limited view of the world, but I'm not going to talk about things like events that occur without an actor and so on. We'll just limit it to the kind of situation calculus that they were concerned about. It's plenty rich enough a domain to introduce the frame problem. So anyway, here's an example. Fluent, we can do a go-to in situation S from X to Y, and then, X does a go-to Y, okay, in situation S, and then he's at Y, okay. If you're at X, Y in situation S, and Y is a bank, and you withdraw from Y some cash in situation S, then you have the cash in situation S prime. This is the situation calculus. It looks a little dumb, right? But that's just because it is. Are these enough to represent change in the world? Well, if I withdraw $100 from the bank, am I on the lam? I'm asking the advice taker, what's the answer? Do your theorem proving, tell me the answer. No answer. You guys are such a recalcitrant audience. Huh?
I think you're on the booze.
I'm on the booze. Okay, well, I'm on something anyway. Is the sky purple? That is, if I withdraw $100 from the bank. Is the sky now purple? Do elephants now have green tusks? That is the frame problem effectively. In a nutshell, those are examples of the frame problem. You perform some action, the fluent tells you how to change the world. It doesn't tell you how the world doesn't change. That's the frame problem. So it's based on cartoon animation, where in a cartoon you have a frame, there's some action, Mickey Mouse is running around, and the framing of that slide or whatever, transparency, whatever they call it, just stays the same from frame to frame. Okay, well that's all very well. Cartoons work, we don't have any problem saying, no, these things don't happen, unless in the first case you might withdraw in an abnormal way, right? But anyway, in general, the withdrawing money from the bank doesn't have effects on the color properties of different things and so on. So we have no problem with that. The problem is that deductively, from the information available to the advice taker about situation S, and the logical consequences of some applied fluent about withdrawing money, the other things, or the negations of these other things, does not follow. It's not a logical inference. So, all right, how do we specify what stays the same? The naive answer is we just like in cartoons, we introduce a bunch of framing axioms which tell us what's going to stay the same. So, withdraw from implies not on the lam, withdraw from implies elephant tusks are white, withdraw from implies the sky is blue. The problem is there's no end of those axioms. There are infinitely many non-changing properties, and if we really have to specify all of them, well, we're going to be encumbered with this ridiculous specification problem, and we're never going to get anywhere with our AI reasoning. Okay, so the frame problem kills logical inference. Now that's not something that McCarthy and Hayes would agree. Of course it doesn't kill logical inference. It kills logical inference as the one and only answer to AI. It shows that there's a gap that needs to be filled, that the induction problem can't be resolved simply by pointing out that induction is algorithmic. We need an algorithm that will do it, that will tell us about things that are staying, things that are changing, as is appropriate to the circumstances. A generalization of the logicism of McCarthy is the physicalism, if you like, of Newell and Simon. So they famously produced this hypothesis in the Communications ACM in 1976, and it kind of encapsulated the American view of artificial intelligence, the physical symbol system hypothesis. So here it is in a nutshell. It says, a physical symbol system, this is their words, a physical symbol system has the necessary and sufficient means for general intelligent action. Now, if you take necessity and sufficiency strictly in the logical senses of the word, this really isn't going to fly, but they didn't. The necessity was literal. That is, in order to have general intelligent action, according to them, you really do strictly have to have a physical symbol processing system. Nothing without that is going to be intelligent. On the other hand, the sufficiency wasn't really literal. There are lots of physical symbol processing systems which aren't intelligent, and they would have conceded that. They did concede that. They weren't arguing otherwise. What they were trying to say was that physical symbol processing systems of the right type can be enhanced to the point where they become intelligent, which is a curious take on sufficiency, but there you go. They wanted a nice label for their hypothesis, and they got it. Okay, so this is the tradition, the logicism and the physical symbol system hypothesis, symbolicism. That was what Hubert Dreyfus was always arguing against. He started very early in 1965 with a Rand paper called Alchemy and Artificial Intelligence, obviously positing some sort of equation between the two. So he had lots of objections. I'll just mention three that are perhaps more prominent than others in his writing and in responses by the AI community and elsewhere. So the embodiment objection points out that human thinking is embodied. There's no such thing as disembodied human thought. But the essence of computation is the opposite of that, actually. The essence of computation is universality. You can take a computational process and transform it, put it into any other computing device that's universal. So contrary to Hans Moravich and others, uploading or downloading our intelligences is a pipe dream. A pipe dream with some very strange stuff stuffed into the pipe. However, uploading and downloading machine intelligence happens all the time. You do it all the time, probably. I do it all the time. So the two are just intrinsically different. Machine intelligence, whatever that is, can actually be transmitted across a cable, and human intelligence cannot. The context objection. He points out repeatedly, Dreyfus, in his writing, that human thinking has a holistic context. It has a story, it has a continuity. Computers, on the other hand, operate by low-level rules, which are just context-free. No such thing as computer context. So when waking from sleep, or even when awakening from a coma, humans have a context that conditions their thinking. The skill objection. This is kind of nice because he can invoke lots of little anecdotes which support it. Human intellect is an inarticulable skill. Computer intellect involves rule following. So, like I said, there are all kinds of examples. So, bike riding, for example. You can describe to somebody who doesn't know how to ride a bike rules about riding a bike. And you can get that person to memorize the rules and test them on it, give them final exams on it, and they can respond perfectly. They know the rules flat out, okay? And then you take that person for the first time and put them on a bike. How good are they going to be? Not very. So bike riding isn't just a bunch of rules. Another example he liked was chess, because chess has the exact backward story you would expect if rule following were the heart of intelligence or intelligent chess play. The rules come first when you don't understand what the hell's going on. You start learning things like try to acquire control of the center, increase the mobility of your pieces, protect your king, and stuff like that. Does a grandmaster pay any attention to these rules? No. Of course, the grandmaster plays so that the rules are in some sense satisfied, because the rules aren't completely brain dead. But on the other hand, any grandmaster is not going to spend even a microsecond thinking about such things. They think about all kinds of other things. So the rules come first when you don't understand, and when you do understand, there aren't any rules. So it's kind of the opposite of the AI story. In general, human implicit understanding trumps explicit representation in almost all domains. And I absolutely agree with Dreyfus about this. There's a marvelously insane paper by Herbert Simon called "Why Should Machines Learn?" published around 1980. And in that, he denounces machine learning. He says in that paper that trying to get AI to learn is trying to get AI to mimic all of the worst aspects of human nature. And amongst other things he says is the opposite of this, which I think is so monumentally wrong-headed. It's just amazing. He says that most human knowledge is acquired through books. Lectures and books and sentences, propositions, you hear the proposition, you memorize the proposition, you take a test, you pass the test. Okay, that's human knowledge, according to Herbert Simon. But surely if we did some sort of measure on the information content of a human brain, we would find things like the taste of real Coke as opposed to new Coke actually occupying at least as much space as anything about relativity theory. Our knowledge of how to move about in the world, how to locate ourselves, how to negotiate, how to interact with people, all of this stuff that we've acquired implicitly over a lifespan of experiences outside of a classroom and not reading books, surely that occupies an awful lot more of our neural capacity than whatever it is we picked up from books. Simon is dead wrong. Dreyfus is absolutely right. So much of the history of GoFi, what is GoFi? Good old-fashioned AI. That's the McCarthyism, that's the Dartmouth program, that's the AI at 50. Much of the history of GoFi reinforces Dreyfus's points. The retreat to micro-worlds and expert systems in the 60s and 70s, that retreat was based upon simply the flat-out failure to do general-purpose AI. They turned to special-purpose AI, something they could actually conquer. They could conquer toy worlds. They could conquer blocks and pyramids and moving an arm around, picking it up and dropping it on another one. They could do that. Whoop-de-doo. The failure of Lennett's Psych project to do anything but waste money. If you don't know what Doug Lennett's Psych project, it was a monumental waste of money. He suckered corporations out of hundreds of millions of dollars to build artificial intelligence. His idea of artificial intelligence was that you get this giant cauldron, you find all of the things that AI researchers had managed to do one way or another, representations, inferences, you drop it into the cauldron. You keep on dropping more and more junk into the cauldron. And eventually, the mass is so great, the pressure builds up and it ignites. And that's intelligence. Well, he kept pouring more and more junk into Psych, and it kept sucking up more and more money. And as far as I know, that's where it still is at. The pathetic attempts at symbolic machine learning. Pat Winston doing his near-miss learning of concepts. Tom Mitchell doing his version spaces, which didn't take any account of noise. It was all qualitative. When he realized that there was a problem with noise, he found a way of branching the processes off, one for each possible way that noise could affect the problem, so that you got this incredible exponential explosion of processes that needed to be computed in order to learn any concept. That's documented in his PhD thesis. But Tom Mitchell has recovered from this. He was mentally ill in 1977. He's perfectly sane today. I've met the guy. I can testify to that. He believes now in Bayesian probability theory. But at the time, it was a problem for him. Okay, well, I think Dreyfus is wrong. Of course, he's right, but he's also wrong. He's wrong in his extreme absolutism. It's not the case that artificial intelligence is brain dead, which is effectively what he was saying. It is the case that symbolicism and logicism, taken as an extreme ideology about the one and only way to do artificial intelligence, is, was, and always will be brain dead. That's correct. Okay, anyway, to take the three complaints. Embodiment, well, not even the symbolicists denied embodiment. So technically speaking, the complaint doesn't even get off the ground. I'm not going to worry too much about this, but if you look at the history of AI and so on, there's a long stream of people concerned about embodiment and concerned that Simon and others didn't take it seriously. They probably didn't take it seriously, but at least they did mention it. Rules are context-free. Well, only if you ignore context sensitivity, which is pervasive in computer science. So I think this was just a matter of Dreyfus being ignorant or not appreciating, at any rate, what Chomsky and others had done. Or what computers can represent, even in traditional representations. Skills are not programmable. That was the skill complaint. But here I think we can invoke levels of representation or levels of virtual machine or whatever. If you have rules at the bottom, how does it mean you have anything like the same rules at the top? And artificial life is more or less founded on the distinction between these kinds of levels. But that doesn't mean that the artificial life simulations that we do aren't algorithmic or don't have rules at the bottom. Of course they have rules at the bottom. But that doesn't mean that at the high level they can be characterized as simple-minded if-then-elses. Now Dreyfus himself apparently came to regret his wholehearted rejection of artificial intelligence. Not that he ever said it in that way, but if you look at the Still Can't Do edition of his book, the third edition, and the introduction in particular, which is new, he allows that artificial neural nets and non-symbolic machine learning can evade the objections. He acknowledges it in a backhanded way. He says that these programs in artificial intelligence have yet to fail. He's expecting them to fail. But if they have yet to fail at that point in 1992, that clearly means that his analytical arguments up until that time and including that time have yet to refute. So they don't refute. So he accepts that. So one of the things that persuades him that neural networks might be more effective than traditional symbolic approaches is that they rely upon, at least in the 80s version, they rely upon distributed instead of local representations. Distributed representations are certainly more flexible than local representations. If you recall the McCullough-Pitts nets, every node in the network had a particular interpretation. It was A, or it was B, or it was A or B, or whatever. In a backprop trained neural network, that's not true. The hidden variables may represent something that's identifiable in English as a kind of semantic atom or something, but they need not do so, and typically they don't. In general, around the 1980s, I would say that AI, traditionally, GOFI, was a degenerating research program. And sometime in the mid-'80s or late '80s, it died. It went from degenerating to dead. Of course, even now there are people who claim to be pursuing these kinds of approaches to AI, so it's not dead in the sense that there's no pulse whatsoever. But the prospects of resuscitation are remote, to say the least. Quantitative AI blew away symbolic AI in the 1980s. So part of the reason for this was just that in the 1980s, that's when a kind of turning point occurred, and computation power became available to the masses. Maybe not the masses of ordinary people, but at least the masses of AI researchers. Quinlan's ID3, for example, it was a quantitative technique using information theory to learn classification trees, and it completely stomped symbolic learning, and Quinlan became very famous, and MDL became very famous as a result of that. Artificial neural nets started using backpropagation and became widespread. Evolutionary methods became computationally accessible. I mean, they were invented in the 50s and reinvented in the 60s, and useless the whole time because they required so much compute power that they couldn't solve serious problems. But by the mid-'80s, that was changing. And artificial life took off. All of these things happened in the 80s. And symbolic AI, in terms of, I don't know, the biomass of researchers doing it or something, didn't completely disappear immediately. It took some time, but it's gone by now. One thing I'd like to point out, and did point out to Dreyfus, is that despite the fighting between genetic algorithms and artificial neural nets and those guys in Bayesians and all of those guys in symbolicists, there's all kinds of fighting going on from the 50s right through the 80s, partly because Seymour and Paper's book on perceptrons in 1969 proving some of the representational limits of very simple neural nets. Anyway, all of that fighting actually succeeded Oliver Selfridge's architecture Pandemonium, which basically had all of these things married together in a single computer program. So I think it's kind of amusing that this is ignored in some of the discussions of the history of AI, and in particular it was ignored by Dreyfus. So this is a kind of sketch representing what the Pandemonium was supposed to be. The name is based on hell, so we have a demon at the top is trying to decide something. For example, maybe character recognition is trying to decide whether a letter is an A or an R or whatever. At the bottom, you have some things which are just getting inputs off of cameras or pixels or whatever. And above them, you have feature recognition demons which are applying rules or whatever to try to figure out whether there's an edge here or a curve or a this or a that. So these guys, when they happen to discover, when they have inputs that match a pattern that they're looking for, right, they screech. And so all of these guys are yelling to the next layer above. And along the lines are weights. So some of the screeches are heard better than others. And eventually at the top level, the decision demon decides who's screeching the loudest given the weighting scheme, and says, aha, this is actually an R and not an H or an A. So that's the idea of what this guy is doing. But it changes over time. It learns. The weights adapt according to a reinforcement learning sort of schedule. And furthermore, what the features are being recognized by these guys changes over time according to recombination and mutation. So there's genetic algorithms, there's neural net, and there's symbolic processing as well. There's logical processing because Boolean operators on these guys are allowed. So all of that stuff was in a single architecture. It's a beautiful architecture. It didn't work. That's because none of these things worked that required serious computation power in the 1950s. But still, it was a beautiful architecture, and it showed it showed plain as day that there's no in principle antagonism between these different approaches to cognition. Yep.
Just quickly,
We must be done.
Yes, thank you very much.
Okay, well, that was the end of the interesting part of the talk. And now on to the rest. Indeed, that's sort of the end of the history of AI part of the talk. There's not much time left. So we'll do the future history really fast. So when will we get AI? Herbert Simon famously or infamously predicted in 1958 that in 1968 we would have artificial intelligence. And he went farther than that. He was perfectly willing to stick his neck out. He gave 10 examples of what things the AI would be doing by 1968, so that included Nobel Prize for Literature, World Chess Champion, and all kinds of other things that either have or haven't happened after 68. Marvin Minsky in 70, he predicted within a few years. Turing, as I already mentioned, predicted effectively 2000. You can see Turing's the conservative, cautious fellow in the group. He's saying 50 plus years after the sheer invention of the idea of AI. But still, he was overly optimistic, I think we can agree. But nowadays, we've learned to be much more reticent and cautious and reasonable in our predictions. So Markham said 10 years, 5 years ago. Okay. So that's what, 2017? Yeah, okay. We'll see. Kurzweil, he's more cautious than Markham. He points out that hardware power will equal human brain power in 2019, and machine consciousness, not just AI, but machine consciousness will be following that up in 10 years. And then he produces exponential growth curves in computing power like this. So right around now, we're around an insect brain. Pretty soon, we'll be at a mouse brain, and then a human brain, and then collectively all human brains together. Okay, and he may well be right about that. Moore's law says such things. If you extrapolate Moore's law in a logical way, then that's what you get. Sorry? Is there a question?
Sorry. Just recognize another person.
Okay, well anyway, that's compute power. Compute power may get us there. So when will we get AI? Dreyfus says never. In order to indicate my degree of contempt, I say 500 years. Whereas Moore's law and its relatives argue for exponential growth in hardware capacity, the AI bottleneck is actually software, not hardware. I think hardware is problematic. It may get there, it may not. But software isn't going to get there, not on Kurzweil's time frame. Kurzweil is undeterred. He actually says software productivity is growing exponentially. He doesn't offer any evidence for this. As far as I can tell, he's doing some very basic back-to-the-envelope curve fitting. So if you draw an exponential curve, there's a knee, of course, where it shoots off. And then there's an initial segment. The initial segment is indistinguishable from a linear mapping, and I think that's what he's doing. He sees a line there and says it's exponential. Incidentally, I do think that things are happening, and useful things are happening. So, for example, Bayesian Statistics is currently competitive with orthodox statistics. That didn't used to be the case. Bayesian computation was in the same boat as genetic algorithms and so on in the 50s, 60s, 70s. It just couldn't reasonably be done except for toy problems. But that certainly has changed. Now we have MCMC sampling, and we can solve all kinds of fairly hard Bayesian statistical problems with computers that we could not do before. And I'm detecting that orthodox statistics will soon be uncompetitive. Well, it'll always be competitive in the sense that if you're sitting around with a piece of paper and a pencil in your hand, then you're hardly likely to do serious Bayesian stats. Okay, so it'll be competitive that way. I'll be using sig tests pretty much always, but that doesn't mean that I'm confused into thinking that's the end of the story. Okay, the software crisis is simply that we don't know how to write and deliver reliable programs of any serious size on time. There are lots of solutions. For example, we can move from machine language to macros in assembler. That was a big improvement, a huge jump forward, probably the biggest one we made. And then there was Fortran, which was another big improvement. And then structured programming, and then object orientation, and agile methods, and I've lost track. I don't pay attention to the software industry anymore, so that's why it's ... I don't suppose there's anything very serious to fill in the dots anyway between then and now. So we've made some really tiny progress with software productivity. Oh, there was also fourth generation languages. What a laugh that was. It's just about setting up GUIs without, the effort. Who cares? Fred Brooks, he was right. There's no silver bullet. It's all incremental and sub-exponential in terms of software. So here's a measure of software complexity. This is the Microsoft main operating system. In terms of size, this being a log plot, right? This is actually exponential growth. It's exponential growth in the bloat required or generated by the MS operating system. It's not so clear you want to equate that with productivity. It's more like waste. Waste is growing exponentially. Software productivity is not. If software performance were to be growing exponentially, what we'd really want is algorithmic time complexity to be collapsing exponentially, asymptoting to zero. That's what would do that. Okay, and do we have that? Well, if you look at fast Fourier transform, the best algorithms for them have gone from O(n) squared to O(n) log n. Sorting, likewise. Matrix, not quite likewise. But in any event, they're all negative exponential, all right, but they asymptote way above zero. So the result is productivity or performance is asymptoting and not exploding. Quite the opposite of what Kurzweil is saying, or what Kurzweil would want, anyway. Well, what would it all want? So the moon, right? Getting to the moon, having a human walk around on the moon, the payoff from that was nil. We didn't bring back any resources. We didn't get any great insights into alien life forms, anything like that. But there were heaps of spin-offs, transistor technologies, and all kinds of stuff coming out of that. And I see AI as being effectively the same. So we have Bayesian networks. This is just an n-gram, so it's a number of book titles that match the search, whatever. Starting around 1988, when Judea Pearl published his book on Bayesian networks and technology and algorithms behind improving Bayesian updating so that it became more accessible. This has been growing quite substantially, and this is machine learning, which is growing even more substantially. So these areas of AI, they've been spinning off a lot of technological improvements that are actually useful to the wider world, and it's making an impact around the world. So AI spin-offs continue, and they're highly productive. Dreyfus was wrong. AI is not impossible. At least his arguments didn't nail that, right? Maybe it's impossible, but he failed to demonstrate it. Dreyfus was right, however, and the singularitarians are wrong. AI is as complex and difficult as anything we've undertaken. There's no reason or little reason to think it's imminent. The singularitarians are also right. If or when AI is achieved, there will be an intelligence explosion. There's no reason why a computer program that's genuinely intelligent and understands its own cognitive apparatus, as it must, if we've built it, and we haven't built it by just simulating a human brain, we've built it because we understand intelligence, then our intelligences, being equal to ours, will understand themselves in the same way, and they can conduct research to improve themselves. Unlike us, they can upload and download. So any improvements they discover, they can upload and download immediately, and so they can improve ever faster. That produces I.J. Good's intelligence explosion, and it's not imminent. Because it requires AI in the first place. But as soon as we get that AI, it will be imminent. So that's a real issue. And they're pointing out that there's an ethical issue that goes along with that. There's an ethical issue about creating a robot which is not just as intelligent as you, but because of its inherent features, will very soon be vastly more intelligent than you. But certainly there's an ethical issue about whether we should go ahead and do that. And if we should go ahead and do it, how? The two are related. So I take that seriously, but that's a different lecture. That's AI ethics, which I have given. I've given for Adam, and we'll probably give again here and there. That's it.
we've got a couple of minutes for questions. John?
One of the things that, looking back over a long career, I see is first of all, the elucidation of particular techniques like symbolic logic in the 19th century and so on, where we were moving from psychology, trying to work out what human beings were doing. So I just wonder what you think about the hypothesis that the actual graph of growth of artificial intelligence should be exponential, but asymptotic, in fact, the other way up exponential, so I think it gets closer and closer to human intelligence, because all the time the human beings going to be in the position that they know what the machine is doing. They don't necessarily know the intricacies of it, but they know in terms of the results, and the human beings can use the results that come out of the machines. So I'm asking about how much you think that what we put into artificial intelligence has been based on reflection on our own intelligence, and how much other.
Well, it's pretty much a mixed bag. I think more of it has been motivated by thinking about human intelligence than has actually been copied from human intelligence. So if you look at GPS, Newell, Shaw, and Simon, they were motivated by making sense out of human cognition, and they came up with protocols to record human thinking and trying to compare a trace of their own problem solver with human problem solvers and stuff like that. So they were motivated by that, but the actual search in the search space is, aside from being heuristically guided, is fundamentally brute force, and that's nothing like what humans do. So they were motivated by it, but in fact they didn't copy it. And I think a lot of AI is actually like that.
Any other questions?
You talk about AI having beneficial spin-offs in the forms of Bayesian nets and machine learning and so on. And Judah Pearl's book came out, 1986 or something?
88.
88. But what were effectively Bayesian nets and probabilistic modelling and so on actually is well before Judah Pearl.
Sure.
And in areas where, for purely practical reasons like data compression, there's an international standard based on that by the late 70s and so on.
Okay.
So I don't necessarily, I think that AI has latched on to developments in other areas, but I don't think AI has created these developments.
Well, I disagree. Certainly, predecessors to what we now know as Bayesian nets can be traced into the 60s at least. There were some naive Bayes algorithms and things like that floating around, and people were working on those. And they failed to scale up, basically, which is why, for example, Buchanan and company slipped back into certainty factors, which are like a cheap imitation of probabilistic reasoning because it's computationally tractable, and they could go ahead and apply it and build expert systems based on them, and they had the look and feel of probabilistic expert systems, but it wasn't the right computation by a long way. In the 80s, it's just not the case that Bayesian nets existed before Pearl's work. Pearl was one of the key developers who came up with the algorithms, the message passing algorithm that allowed Bayesian nets to operate. It's true that there were predecessors, of course. If you look at the history of ideas, there are predecessors all the way back that we can go. Presumably there are predecessors beyond that as well, but we just don't know how to look any further. So of course there are predecessors. He was like Newton. He was standing on shoulders of very deep and good thinkers and so on. But it doesn't mean that he didn't add to it. Of course he did.
One more question then, last one.
I'd just like to share something about the optimism of some of these people involved in the area. That you mentioned that Marvin Minsky had predicted 73 would have it, 78 would have it, but he also did it in 83. He did it every 5 years.
I didn't do an exhaustive search.
But I was at an AI conference in Sydney. There were about 1,500 people there. Marvin Minsky got up and he said, 5 years ago, I promised that we'd have this, and we'd have this, and we'd have this, and AI would have reached these goals, and it hasn't happened. And he pointed around at the 1,500 people in front of him, and he said, and it's all your fault.
At least he had a sense of humor. It's good.
That's probably a good place to finish, I think,
Okay.
the official part. So let's thank Kevin once again for his presentation. Thanks all for coming along today, and especially for those of you who've come to several of the seminars. Please, if you have any feedback on the series, since it's now over, maybe I'll do it again one day, incorporating your feedback. Thanks.